All right. We just introduced the idea of momentum, which is inertia in motion. And we also introduced the idea of impulse, which is how much force and how long you apply it um, to make any necessary changes to an object's momentum. And we can revisit that really quick. So that's going to be your impulse, Ft, and then that's going to equal a change in your momentum, mv. Um, So only an impulse external to a system can change the momentum of the system. This kind of sounds like Newton's third law, where only an external force can change um, the acceleration of a system. Okay, so just like Newton's third law, um, internal forces and internal impulses, they won't do anything to your system. They're all going to cancel out. They're going to equal zero. Cancel out. Equals zero. Okay. Um, so if no external force is present, then no external impulse is present. So you'll notice that anytime a force shows up, there could be an impulse showing. This would be no external force, and that means no external impulse, which makes sense because if we look back up here at our definition of impulse, well, that has force in it. So this is impulse, and by definition, it's dependent on a force. Okay, so if there's nothing external acting, then there is not a change in momentum. So no change in momentum is possible. And this guy down here sums up everything nicely. Notice that Newton's third law actually leads to momentum conservation. Okay, so now we're actually linking the stuff from last week, Newton's laws, to what we're talking about now, which would be momentum. Okay, so let's consider this example. Maybe some of you all have done this. You can find lots of videos of it on YouTube, but if you toss a ball horizontally while standing on a skateboard, you will roll backwards with as much momentum as you impart to the ball. Okay, we've seen that with the cannonball example last week, where you shoot a cannonball out of a cannon, and then the cannon is going to feel an equal and opposite reaction. So you can see here in the picture, this is our before shot of momentum, and this is our after shot of momentum. I'm going to write this out. Before, after. Make it a little less confusing about what we're looking at. You'll notice that the skateboarder is going in the opposite direction that he has thrown the ball. Okay, that totally makes sense, but still, this isn't our question yet. So, will you roll backward if you instead hold on to the tossed ball while going through the motions of tossing? So, if you just pretend to throw it and you move your hand, are you actually going to roll backward? And the answer is no. Without an external impulse acting on you and the skateboard, you will not roll backwards. So you're not letting that ball leave your hand. It's still all in that same system. So if no momentum is actually imparted to the ball, then no net force can be imparted to you and the board. So this is one of the biggest ideas in physics. It's just the idea of conservation. We could have conservation of momentum, conservation of energy, conservation of charge, which we'll talk about later. But essentially, the whole idea is that when quantity is conserved, it's going to stay constant. I guess in our case, since we're sort of thinking about physics in terms of these physics problems, our momentum is going to stay the same throughout an entire problem. That means it's going to be conserved. So this is a conservation of momentum approach, and this works for everything. You can actually use this when you're doing astronomy and you're studying galaxies. Conservation of momentum applies. You can do this when you're studying interactions of subatomic particles. Conservation of momentum applies. So just because we're talking about cannons and cannonballs does not mean this is a trivial concept. This is a very fundamental component of physics, and it's a universal law that shows up everywhere. So let's look at this example, which is super simple, and we'll talk about this idea of conservation momentum with this cannonball example. All right, so the force on the cannonball inside the cannon's barrel is equal and opposite to the force that causes the cannon to recoil. So we remember that from Newton's third law. Basically, whatever force came out, we'll call that force one. So this is the force on the cannonball. That has to be equal and opposite to the force pushing back on the cannon itself. So those will always be equal opposite. So I'll put a negative sign in front of the force two. So since the force acts for the same duration, okay, so think about that. However long the force over here is acting, force one acting on the cannonball, that's the same as however long force two acts in the opposite direction. Well, if the forces are equal and opposite and the times are the same, well, then that means the impulses are also equal and opposite. So here we'd have a negative F2. That's got to equal the positive version. These are vectors. So the impulses are the same, just opposite directions. Well, Newton's third law about equal and opposite action reaction pretty much applies here too, since the forces are equal opposite and the times law of the interaction will always be the same. Here's where Newton's third law shows up. So we do see a Newton's third law. And of course, these impulses are internal to the system, and therefore they do not change the overall momentum of the system. Because if we think about how the momentum is going to change, well, everything so far has been equal and opposite. Right, everything's equal and opposite. So the change in momentum is going to be zero. Everything's conserved, and our system is obviously the cannonball cannon system because the cannonball's still in there. So even when the cannonball is fired, it's still a part of our system that we've defined. So in the after situation, this is going to get crowded. In the after situation, we can define our system as still the cannonball and the cannon. We just had to expand it because the cannonball is actually in motion. But the whole point of that is that these impulses are internal. So there's no change in net momentum. Momentum obviously is a vector quantity because it is mass times a velocity. Mass is not a vector quantity, it's a scalar, but velocity is a vector quantity. So momentum is a vector quantity. It's got a magnitude and a direction. And that means if we have two momenta pointing in opposite directions, but with equal magnitude, so if they had equal magnitude, opposite directions, we could have two different momenta that cancel out. So in our case, the momenta of the cannonball and the cannon, those are actually equal and opposite. So that's why they're canceling out. And that's why we have this statement down here, the change in momentum equals zero. Again, just to reiterate, any quantity in physics, like net momentum, does not change, we say that it is conserved. And this leads us to a formal statement of the law of conservation of momentum. Very important physics used all the time. So in the absence of an external force, okay, no external force, just like in the previous cannonball problem we talked about, the momentum of a system remains unchanged. Okay, so no change in momentum if there's no external forces. In any system where all the forces are internal, the net momentum of that system before and after are also the same. So if we are clever about how we set up our system, that means any initial momentum that the whole system has to equal the final momentum. So whatever happens in between an interaction, the momentum's got to be the same. So let's think about this in terms of a cue ball hitting an 8-ball head on. Okay, so when we go to the next slide, remember that the cue ball is in motion. Oops, let's call this the C for cue ball, and then the velocity of the 8-ball is 0 meters per second. Okay, it's sitting at rest. So if we think about the 8-ball as our system, okay, and our system is just the 8-ball, okay, well, we can see that in this first picture. So an external force would act on the 8-ball system. So the question is, why is this all of a sudden an external force? And we just talked about how systems have equal and opposite internal forces. Well, look at how we defined our system. I've circled it here in green. The 8-ball is our system. Okay, so we've blocked out the cue ball. It is now external. And that's just because of how we set it up. Okay, we could set this up any way we want to. But in this example, we define the 8-ball as our system, which means we have an external momentum coming in. Now, how does that change our system? So it increases the momentum of our system, which is the 8-ball. Right, so the momentum increases in our system. Okay, so our 8-ball is just chilling. All of a sudden it gets hit, and just looking at our system, that 8-ball actually gets more momentum from the external cue ball. Now, if we think about this in terms of the cue ball system, again, we can draw our system however we want to. So if we think about the cue ball system here, okay, so we're sort of following along the cue ball with our camera, and we don't know much about the 8-ball, but okay, we have this cue ball. It's moving, so it does have some initial momentum. Right, in the previous example in our system, our 8-ball was just sitting there, so no momentum. Now we do have some momentum in our system because we're looking at just the cue ball. Now, when this cue ball that's moving hits the 8-ball, well, obviously it's going to slow down. So we're going to have a negative change in momentum, right? Because it's got some speed, it hits the 8-ball. Well, it's got to put some momentum into the 8-ball, right? We can see that here. So actually, our system this time is going to lose some momentum to this external component, which means it's going to slow down. So depending on how we actually define our systems, you can define it one way, like here on the left, where the thing we're looking at will get an increase in momentum. You can define it, right, how we've done it on the right, the thing we're looking at loses momentum. Or we could define the whole thing we could define the whole thing as our system. And then since we have one subsystem where we're gaining momentum, one subsystem where we're losing momentum, if we look at the both balls together and use this as our system, then now we see momentum is conserved, right? So whatever happens to one of them gets transferred, but it's still inside our system. So now we actually get no change in momentum. Okay. Now let's actually think about doing some calculations for these collisions. So we have momentum, which is being conserved in collisions. If we draw our system right, this means that the net momentum is unchanged before, during, and after the collision. So now that we're conserving momentum, we get this nice statement here. The initial stuff we start with, the net momentum before, has to equal the net momentum after. So the idea is that there's only a redistribution. So if you've got 2 or 3 objects over here and they go through some sort of collision, net momentum is the same, but they may have transferred some momentum between each other. But when you add them up, they'll be the same. So there are 2 ideal types of collisions. You have one, which is an elastic collision. So this is basically 2 objects that collide and they don't deform each other. Because if you hit a car and you dent the car, you're actually losing some momentum in the making of the dent. So the idea here is that if you have 2 objects like billiard balls or bowling balls and they collide and they rebound without generating heat because that's energy loss, or if they don't deform each other, if they're really solid, that's the idea of an elastic collision. Now, an inelastic collision is the exact opposite. Okay, so these things come in and smash together and then stick together. So these are 2 ideal collisions. And the whole point of this word ideal is these 2 are the mathematically easiest to deal with. Okay, so they're easy to deal with. We have a perfect hit and bounce off, and then we have a perfect hit and stick together. But the thing is, most real world collisions that you're going to see, like in a traffic accident or something like that, most are in between these two types of collisions. So you might get 2 objects hit each other, they deform each other a little bit, then they kind of bounce off. The whole idea of these ideal collisions is it makes the math simpler. And what you do when you are trying to model one of these situations out in nature is you pick one of these 2 ideal instances that your situation is close to, and then you can use that as a simplified model. There's ways to include more complicated collisions, but we won't get into that in this class. So just know that there's 2 rosy, peachy examples of collisions, and you just pick the one that's closest to what you're looking at. If you're interested, you can take the other physics courses at LR and learn how to deal with more complicated collisions. So when we think about these collisions in one of these 2 instances, we also think about the time of impact being short, right? So a pretty high impulse due to the short time, or a pretty large force due to the short time. So generally the time is short, which means the force is great. And since it's a large force, generally what we'll do is we'll sort of ignore the friction during the collision. We can take into account friction after the collision, but just over that short time and some big forces at play, we won't worry about what friction is doing. All right, so let's look at some quick examples. I think I've got 3 in a row that will follow up with some notes on more complicated collisions. I think it's like 1 slide, and then we'll call it. Okay, so a fish swims toward and swallows a smaller fish at rest. So we know this fish swimming this way This fish is not moving, okay? If the larger fish has a mass of 5 kilograms, okay, and swims at 1 meters per second toward the 1 kilogram fish, what is the velocity of the combined masses just after the interaction? Okay, so we're going to start with two separate masses, but this big fish is going to eat the smaller one, which means they're going to have a combined mass. They're going to be one object afterwards, and they're going to have combined mass. Okay, so the net momentum before, we have two objects. They both have masses, they both have velocities, 1, 0, but they both have velocities. After the collision, we have one object. Okay. So now let's think about the net momentum. Okay, so we have two objects to deal with. This is the before side. Okay. So here's our two momenta we're adding together for the before side. Now, we know that the initial one is going to be 0 because it's not moving, or the small initial value is going to be 0. Already got that plugged in. So that's good. Now we just have to plug in our mass, our velocity for the big fish. So in the before part, all of the momentum in our system, our two fish system, is coming from the big fish. Okay, well, that's the before side. Now let's think about the after side. So in the after side, since the big fish has eaten the small fish, they're acting as one object. So now we have to add those masses together. Since this one object is the mass of the big fish plus the mass of the small fish. And since they're acting as one object, we don't have separate velocities for them anymore. They're moving together, so they're going to have one final velocity. So this is essentially the same for both. Okay. And this is, you can think of this as just big M, total mass, times velocity. All right, so we just plug in those values. I'm going to change this to black. All right, so we can do some quick algebra. We know that this is going to be 5 kilograms meters per second on the left equals, this is going to be 6 kilograms meters. Oh, no, just 6 kilograms times our final velocity. Now to solve this, we want to get V by itself, right? This is what we're solving for, final velocity. You can see, just divide both sides by 6 kilograms, and you will get, for the final velocity, 5.6 meters per second. Now notice it's positive. So the final velocity is in the positive direction. So this fish does slow down. Remember, it was swimming at 1 meter per second. But then it slows down to 5.6 meters per second. So what happened is it's got some velocity, its mass changed, and because it has an increased mass, it's going to slow down. It has to slow down a bit to compensate, right? Because you want your momentum to be the same. Well, all of a sudden you've got more stuff to move. So to make sure the momentum stays the same, more stuff means less velocity. So the whole idea is that the mass went up. So to compensate, the velocity has to go down. But we're still, so far, moving in the same direction. All right, let's think about another scenario. In the previous one, the small fish had no momentum since its velocity was 0. After the collision, the objects had the same velocity, but what if the small fish was originally swimming toward the large fish at 4 meters per second? So let's say everything was the same. So this was a 5 kilogram fish swimming this way at 1 meters per second. This is a 1 kilogram fish, but now it's going to swim to the left, the negative direction, at 4 meters per second. So what happens now? Now they're actually moving toward each other with two different velocities. We can do the same thing again. We've got our before situation, and we have our after situation. And when you're doing momentum problems, this is always a really good way to set it up. Do before crap, set up your equations, equals after crap, and set them up equal to each other. So we have our big fish, 5 kilograms, 1 meters per second. Again, this is just mass times velocity. Same thing, except remember this small fish is moving in the negative direction because we just arbitrarily chose this to be our positive. We could have done all the math with a different positive direction. We could have had it pointing to the left. All the math would have worked out the same. It would have just changed all the signs on every term. So if you notice some weirdness, if you're doing a problem set problem, you might have just picked a weird direction for your positive direction. Totally fine, follow it through, and you'll most likely get the right answer anyways. But anyways, we've got our before done. We have our big fish, little fish. Now we have our after. Again, big fish is eating the small fish, so they have a combined mass in the end. They have one velocity, right? That's what we're trying to solve for. And I won't walk through all the algebra this time, but what you'll notice is this time, now that the small fish, instead of it just sitting there, now that it's opposing the green fish's momentum, we actually have an even smaller velocity, right? This is only 1/6 meters per second. So this is actually even smaller. So now the question is, what can we do to actually change the direction of travel? Once this big fish eats the small fish, how can we actually have the combined system move in the opposite or negative direction? So in the past two cases, the combined masses moved in the same positive direction of travel. Okay. How fast does this fish need to swim in order to actually, once the big fish eats it, the little fish had so much momentum that it actually pushes the green fish back in the negative direction. So again, this is our positive. What we want to do is, what is it going to take to get this combined system to go in the negative direction? So again, we have our before, we have our after. Now that you've seen two examples of this, I can go through it faster. So let's say that this fish now is traveling at -8 meters per second. So it's going really, really fast. And then the green fish is going to stay the same at 1 meters per second. Okay, well, let's see what happens. So here we have our green fish. Everything's the same, 5 kilograms and 1 meter per second. Okay, now we dump in this other momentum. Notice that it's going to be a -8 meters per second because it's traveling in the negative direction. Okay, and then same thing over here, same masses, solving for this V final. Well, look at what happens now. Suddenly our before momentum is a net negative. That means when we take our before snapshot, the little orange fish is moving so fast that even though the green fish is moving in the positive direction, the total momentum is being dominated by the orange fish. So this right here, because the total momentum before is being dominated by the orange fish. That'll be the -8 meters per second. Now when we solve for V, we finally get a negative velocity. So finally, after traveling 8 meters per second, the velocity after the collision is pointing in the opposite direction. And we know that because our final velocity is negative. So just to think about some more complicated collisions, we have essentially the net momentum remaining unchanged in any collision, regardless of the angle between the points in the paths of the colliding objects. So whatever the nature of a collision, or however complicated it is, the total momentum will still be unchanged. So you can see up here in this example, we have two cars that collide here. Each one obviously has a momentum. So this is car A, this is car B, and actually when they combine, we have two momenta. Remember, momentum is a vector. So we have these two separate momentum vectors, and we just combine those. We add those up like regular vectors. So just like always, we have the two vectors here. So we have momentum of car A, momentum of car B, and then we use the parallelogram rule or tip to tail method, whatever you want to call it. So I'll slide the B vector over. So this is the tip to tail method. So once I put them tip to tail, I just connect the starting point to the ending point. So it looks like our net momentum after, so if this is before, this is our net momentum after. And it turns out, even though we have two different momentum vectors pointing in two different directions, and then afterwards in this inelastic collision, because they're sticking together, afterwards we only have one momentum vector, but it's the same, right? We can break this down and show that two separate momenta added together equals this one momentum afterwards. So even in this crazy setup here, momentum is still conserved. So this is useful to learn. This idea is useful because we can learn about what's going on in the dynamics of a situation, even if we don't know about the forces acting on it. And this also applies to exploding objects. You can see here, this is our before. One object, then we have this explosion. So then we have an after. So we're going from one momentum vector to two momentum vectors. So essentially, this piece here is going to have its own momentum. So we'll call this piece one. So this is going to be the momentum of the first one is flying off to one side. And then the other piece of this thing after this explosion is going to be flying off in a different direction. So we'll call this two. So even though we're going from one momentum vector to two momentum vectors, you can still add them up. You can still show that even here, the before and after, if you add up all the vectors, is the same. So that actually, if you have a debris field and you know where some things are, and you know some of the momentum vectors, you can actually back calculate and find the unknown momentum vectors and essentially find more pieces of a debris field because you know momentum's conserved and you know that all those things have to add up to the momentum right before the impact of whatever object it is. All right, so that's finished everything as far as conservation of momentum and collisions. I think the next lecture will be just lots of examples and sort of some real world applications of the idea of conservation of momentum.